analog of the tensor representation. The analog of the tensor representation is that now the homomorphic, because this object, this tensor belongs to the tensor power, but not the symmetric tensor power. Okay? And this is again in Hn. So we have now that simply in this isomorphism, we simply replace symmetric tensor power. Here we replace the usual tensor power by symmetric tensor power. I want to emphasize, this is the standard tensor product. This is the symmetric tensor product. But this is the standard. So by permuting this standard, I got symmetry. This is usually done in boson case. Okay. Now, what is L star in the analog of L star? The analog will be the symmetrized of L star. So we will denote like L symmetrizing V applied to a vector V n tensor, etc. Tensor V1, by definition, it will be, well, here I don't take, because I want this map to be, I will not take the normalization like in the vectors. Okay? So I will take sum. Well, in fact, it's the same. It's implicit. It's implicit. So it will be Vn tensor this is a special. Sorry. I have the other order of the numeration. And J goes from 0 to end. Well, if here, when J is 0, I am going in the opposite direction. When J is 0, here you would have V minus 1. So by definition means that there is nothing when you have an index V minus 1. Okay? I don't write explicit. It's just a notation.
But don't you need symmetrizer on the left?
What?
E n tensor. You update on the symmetric space, right?
Right. And because you see, this is just a symmetrized form. Because this will be when put a J equal to no. So that this is. So I have to do like this. I have to go from 1 to n. From 1 to n, and let me write explicit because I see there is a confusion. So when J is equal to n, I should be n minus 1, but the n minus 1 is V.
Your original vector has to be symmetric to begin with. That has to be symmetric to begin with. Right?
Yes. This is symmetric. Yeah. This is symmetrized. So this is well. Let us do so. I want to do. Let me do in a simpler way. In the notes, I didn't give this proof. I gave this proof. In the notes, I gave this proof. I use a known fact that by the polarization identity the tensors of this form are a linear set of generators in the symmetric tensors. That is, any symmetric tensor can be written as a linear combination of tensors of this form. This is a well-known fact. This is I will, if you want, I put in the appendix the polarization identity for commutative rings that we are using here. It shows that if you have a symmetric and linear map, then it is uniquely determined by the diagonal. Okay, so, but this is, so in this sense I will write that this is, and then the formula I wrote before is correct, because it will give me U tensor, H tensor, V tensor, U power n minus 1 minus n minus. Maybe I can let me check this. If I put n minus j, when j is n is 0, so it means nothing. And when j, when sorry, h. When h is 0, this is u power n, and the first is v. When h is n, there is nothing here, and then the convention must be that u tensor power 0 by definition is v. So essentially this means for h goes from 0, no, because I have put v here, so u tensor power tensor v tensor etc by definition is v tensor etc. This correct now? This, as you know, is clear. So if something with the power tensor power 0 come, I simply don't consider it. Okay, so concretely, how can we write this? We write v tensor u power n, tensor power n, and then plus, it must be symmetric, simply this, u tensor v tensor u tensor power n minus 1, plus, etc., 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 and then what you will have? You will have u tensor n times tensor. So this is the explicit form. So this is for the symmetric case. So now what we want the analog of, so we want the analog of this example. This example characterizes what?
So the right hand side will have a tensor hat.
Huh?
The right hand side of that equal to last line. Yeah. On the left. The last line.
This one?
No, on the left. This last
The
line
right hand side.
of the equal to.
Ah, this is not plus, it's plus.
Okay.
Yeah, sorry. Thank you. This is plus. Yeah. So now this is the symmetric. So this one is called the free Fock space or full Fock space. Or also called full. Sometimes in the literature you will find this name. Okay. Now we will arrive to this theorem extended to the symmetric case. What will give? Will give the tensor representation, we arrive to the Fock space given by the sequence. The gradation is given by the symmetric tensor powers with the scalar product, which is now given by the symmetric nth tensor power and with the free symmetric creator. And what is the symmetric tensor power? Again, I will use this trick to use the linear generators. So I will say that a U tensor n times V tensor n is by definition UV. Okay, so this is what is called the boson-Fock space. You see, it's a very special, so this is what we call the tensor product, tensor symmetric N. So this is a very special interacting Fock space. So you understand what is the generalization, what I mentioned in one of my previous lectures. This definition of interacting Fock space is essentially, as you see, I have only two axioms. I have a gradation, and in fact I should write three, because when I write it belongs to the adjointable, is a third additional condition. So there is a gradation. There is a creator, which is the gradation increasing, and the creator is an adjoint for the scalar. So you see, if you give arbitrarily this, let us take now the simplest example, the full Fock space. So the creator is defined by this. Is defined by this. The free creator. By this condition. If you put arbitrarily the n plus one scalar product, the n scalar product cannot be chosen arbitrarily, because there is a constraint. The simplest constraint is that this condition that it is adjointable means that if I take the creator acting on the nth vector and I compute the scalar product with a n plus 1 vector, the n plus 1 scalar product, this must be equal to the annihilator acting on eta n plus 1 multiplied by Cn, but this must be in the n scalar product. And so you understand that if I choose arbitrarily, suppose that the spaces are finite dimensional, I always, since the space, the scalar product is on a finite dimensional vector space, this will always have an adjoint. But the adjoint for this scalar product can be completely different from this. Okay? So it's a strong condition.
But the adjoint will be defined that once.
The existence is a strong condition. The existence of the adjoint is a strong condition on the sequence of scalar products. It's a big constraint. And we will study in the theory of multidimensional, that I will begin next time. And if somebody wants to go a little bit further in one dimension, I am ready to do with great pleasure, because there is a lot of things that I have jumped. Some of them are very interesting. I am afraid that we will not have time. I wanted to explain to you today, in the second part of the lecture I prepared, I want to explain why when you want to do the analog of the Weyl operator in the one-dimensional case, you begin to go in a more subtle level of the theory. Because you remember that we proved that we have the commutation relation in one dimension. We have the commutation relation that A minus A plus is equal to D omega lambda, okay? And of course, if D omega lambda is constant, like in the Gaussian case, Heisenberg commutation, of course, if I put the identity in the identity is a central element, it commutes with everything. But this is an operator. So I can only, and we know the commutator with this. Then the commutator of A dagger with the lambda must belong. And the commutator of commutator, and so on. So, in general, you will have an infinite dimensional algebra. When do you have a finite? And there is a very nice condition. You will have a finite dimensional algebra if and only if this sequence omega n has the form of a polynomial in, so for each n greater than a certain capital N that depends on the sequence omega, omega n will be a polynomial in the variables omega k, which k less or equal than n. And so essentially, the first n omega elements of the sequence uniquely determines, well, this polynomial depends on n, of course. The first n omega, capital N omega, determine all the others. So, it's a simple, very simple sequence. It's a system it's a sequence which I can produce with a computer program. If you remember the idea of Kolmogorov to define complexity, that I can produce a sequence as low complexity if I can write a program to produce it. And Kolmogorov proposed a measure of complexity of sequences using the length of the program, the minimal length of a program that can produce the sequence. So random sequences have infinite complexity. Okay? These sequences are the simplest because they have finite complexity. And so we used with Riemann and Barumi this idea of complexity to describe how complex is a probability measure. And not by chance we found the simplest measures are classes that in some sense people met in some central limit theorem, in other fields. Roughly speaking, these measures are those in which the omega n grow polynomial in n. Okay? So the Gaussian is polynomial of degree 1. The Meixner, polynomial of degree 2. What happens degree 3 on, and you will see why. If you are interested, I can give you more details on this to show why 2 is a critical dimension. Because 2 is the highest degree of the polynomial, such that the Lie algebra generated by the commutation relation is finite dimension. 2. Starting from 3, infinite. So I think, I'm sorry, I was a little bit further, but there is another conference after. Yes, so we have to. maybe if there are questions we can do during the
Yeah,
outside.
So what is this real